Okay, thanks Pedro, and thanks for organizing this workshop. I'm going to be talking about some work done with Simon Knapp and Tim Liu and Tom Melia. And the idea is that we can use heavy ion collisions to actually do some BSM searches. So what we looked at was how to exploit the photon-photon luminosity in heavy ion collisions to look for axion-like particles which couple to electromagnetism. And we can be sensitive to those axion-like particles, ALPs, in the mass range of 1 to 100 GeV or so. And just briefly at the end, I'll mention some separate work I've done on looking for very low mass axions in B factories. So the rough outline will be that first I'll give an overview of some heavy ion, the heavy ion program at the LHC, which not everyone is necessarily familiar with. Then I'll move on to using the photon-photon luminosity. So this is the main point we want to exploit in heavy ion collisions. And then the particular signal and signal backgrounds. And I'll discuss, for instance, there was, after our paper, a few months after our paper, there was an ATLAS result on diphotons in heavy ion collisions, and we were able to recast it and found fairly good agreement with our projections. And so I'll just show those projections and discuss the broader model space for ALPs at a GeV scale. Okay, so probably most people in this room are more familiar with proton-proton collisions at the LHC, but all 4 experiments are participating in heavy ion collisions as well, or plan to participate. So this includes lead proton collisions as well as lead-lead collisions. And these are heavy ions, just as a reminder, for lead. Okay, so the center mass energies are expressed differently for the heavy ion collisions. So we have the same, LHC, so these, now the energies get scaled by the mass to charge ratio of the heavy ion. So instead we get something like 8 TeV per nucleon is the relevant parameter. And this is 5 TeV per nucleon. And this is much higher energy than the previous heavy ion experiment, or the previously running one, which was RIC, with center mass energy of 200 GeV per nucleon. So these are the highest energy heavy ion collisions. Of course, you might start to ask about luminosity. So here's typical luminosity for proton-proton, whereas for these heavy ion collisions, we get orders of magnitude lower luminosity. So this is of order 1 inverse nanobarn. This is of order, say, hundreds inverse nanobarn. So for instance, the ATLAS result that came out was based on a run in 2015, the heavy ion run in 2015, with 0.5 inverse nanobarn. The next time they'll do it is end of 2018 with probably similar luminosity. Do they have, sorry, what? No. Yeah, so I was just about to say that. So this is a fairly low luminosity, but there are a couple of ways we can we can still use this effectively. One is that there's essentially no pileup, and we can have very low PT triggers. So that's what's allowing us to look for sub-100 GeV axions effectively as compared with PP collisions. Additionally, we can make up for this reduction in luminosity with photon-photon collisions, where, as I'll discuss, we'll get a large z to the 4th enhancement. So this is 5 times 10 to the 7. I'll get to that, but the photons are coming off the lead. And the last thing we'll use is that we can have ultra-peripheral collisions. And that means that instead of the very the extremely high multiplicity head-on lead collisions that we usually think about when we think about heavy ion collisions. We also have grazing interactions where the lead ion doesn't break up. And so those are extremely clean events where essentially whatever is in the final state is just, for example, photons or a couple electrons or something. Okay, so let me talk about these ultra-peripheral collisions. Okay, so again, the usual thing we think about are these face-on collisions with like 10 to the 4 tracks or something. But in the ultra-peripheral collisions, we have just lead. They don't break up, and they just go down the beam pipe. As an example process that has been looked at, here, this is a photon. These are gluons. So I have 2, so I have no net color exchange. This is CC bar. Okay, so there's a study of ultra-peripheral collisions producing J psi. Final state is muons. And that's really all there is in the event. So if you look at an event display, there's these 2 muons and nothing else. And so this is something that has been done with both ATLAS and CMS. And so there's a slight difference to the usual. So you can use the full ATLAS CMS detectors. And there's an additional tag you can put to make sure that there's really nothing else in this event. Okay. So this is ATLAS or CMS, let's say. And here's like various segments with muons and HCal. So in doing the heavy ion collisions with ATLAS and CMS, you also place vetoes on forward activity. So there's 2 things here. One is, well, I don't remember the exact name, but so it's a forward calorimeter where you want to veto on any activity here. And then here, there's also what's called a 0-degree calorimeter. This can detect neutrons. So occasionally this lead nucleus does get excited and emit, say, a neutron. And so that's an additional way to tag these ultra-peripheral collisions. Okay, but so otherwise you get the entire power of the ATLAS and CMS detectors, and then you just put vetoes or tags here down the beam pipe. No. Yeah, the most they do is tag the neutron. Okay, and because this is such a clean event and we don't have the same problems with pileup, these muons can be detected with fairly low thresholds. So for instance, these will be like GeV. These muons will have momentum of order GeV, and you can get an energy resolution of order, say 100 MeV or something, or even less. Okay. So one of the studies that's been published looked at this final state, and for instance, you can look at the invariant mass spectrum, and it's a very sharp peak, which clearly shows that there's this J psi here. The actual rate of this is hard to compute, and I think it's just a free parameter that's being fit. In addition, these muons are pretty much, where's the almost back-to-back? So if we look at the PT of the muons, this is something that for these ultra-peripheral collisions and in the coherent regime is highly peaked at this net momentum being 0. So this is the scale is about 0.1 MeV, and above that it's suppressed. So we'll have something similar for the diphoton signal. So it's a fairly simple analysis in that that's all there is, and the main additional cuts you want to put are to have them very close to back, so that there's no extra forward activity or additional activity. How rare? The cross section for this is pretty high, actually. I mean, there's plenty of events. Yeah, the measurement of that mass peak is very good. Okay. All right, so that's an example of some of the existing analyses. What we wanted to use was the fact that there's an extremely large rate in ultra-peripheral collisions with the photon-photon luminosity. This is kind of noisy. Okay, yes? Is there equivalent what? No, there isn't. Well, there's a rough scaling of, I think it's estimated to be a to the 1/3. Yeah. Yeah. Okay, so the basic process that I'm going to be looking at is just photons initiated by these lead ions going to an axion. And my axion coupling is just this. So what I want to use is the fact that there's in the limit where these photons are sufficiently low energy, I can get a coherent enhancement and have a z to the 4th, again that 5 times 10 to the 7 number in the luminosity. So the conditions under which I can get this and then get a large enough rate are the following. So for coherence, if I look at the ion in its rest frame, then I want a photon wavelength to be larger than the size of the ion. So this is for ion. And for lead, I'm just going to state the number. And so that means the energy should be less than this, which is of order 50 to 100 MeV. But if I boost this now to the lab frame, I get, so the boost factor is about 3,000. So now the condition for coherence is that the energy of the photon should be less than roughly 100 GeV. It's very close to on-shell. I'm going to use the equivalent photon approximation. So if that's, yeah. Yeah, so I'm going to use the equivalent photon approximation where I just neglect the kinematics of these, of the ions themselves. Okay, so actually, I can also do the same thing with protons. So there is a CMS result on proton-proton ultra-peripheral collisions initiated by photons, for instance. And here the radius is of order femtometer, which means I can get to even higher energies of order TeV, but without the z to the 4th enhancement. So these lead-lead collisions, because the center of mass energy per nucleon is so high, I can actually get this coherent enhancement for ALPs as heavy as 100 GeV. And this makes this also an extremely powerful, essentially flashlight of GeV photons. Okay, so I will go up to 100 GeV. Mm-hmm.
So I follow the numbers. So how are we going from wavelength to? So a Fermi is 200 MeV.
Yeah.
So where's the other?
So
Factor
this factor? No, the boost. You mean the boost? Yeah. Sorry if I. So now this omega becomes gamma over ion. So omega lab is less than gamma over ion. Yeah. Yeah. So for protons, I win a little because the radius is smaller and I get bigger boost. Okay, so the nice thing about this this process is I can compute everything almost analytically and get a very good approximation. So I'll try to give some analytic scalings for this. Okay. Okay, so if I look at the electric field of a charged particle, and this charged particle is moving very fast, then the field lines get squashed, like so, from E and M. And the equivalent photon approximation, or the Weizsäcker-Williams approximation, which is what I'm going to use, treats this incident flux, this incoming particle as nearly on-shell photons, a pulse of nearly on-shell photons, which is just the pulse of this electric field passing by. So for instance, here's the ion. If I'm looking here, so this is the impact parameter B, then what happens is that as the ion goes by, here I see some pulse in the electric field, which I think of as some flux of photons. And so that pulse that I see here is just given by the electric field squared, so it's just the energy density in the field, where I took the Fourier transform to get the energy spectrum. So when this is the impact parameter with the collision point. So I'm going to integrate over all impact parameters at the end, for instance. So when this, in the limit that this is moving ultra-relativistically, this pulse just looks like a delta function in time, right? So at t equals 0, I just see a delta function in this in this field. And for a delta function, we know that the Fourier transform giving us this energy that will give us this Fourier. Sorry, the Fourier transform is just a constant. So what I get is that the energy density is just independent of this of the energy of the photon. Okay. And then to actually get the photon PDF, what I want to do is integrate over all impact parameters. So I can define something as a function of the photon energy again, which is just integrating this flux over all impact parameters. Okay, so from this, I get, yeah. Because of the light? Okay. Yeah. Yeah. Okay. Yeah, sorry. So this was my incident flux, which was the energy density squared. I argued that's constant. And then now I want to integrate over all impact parameters to get a photon PDF effectively. Okay. Okay.
Thank you.
Okay, so I can do this integral. It's just a log. So again, everything's very simple. I just have the z to the squared, the alpha, and some log. And the piece where I account for the fact that this is a heavy ion and not a point mass is that I want to take a minimum impact parameter, which is given by the ion radius. So I don't want to look at impact parameters such that I lose coherence. Yeah. Yeah. If you're too close. Yeah. So it will fail if it's anytime you care about the kinematics of the ion in the end, or if it's moving too slow. Yeah. So this dependence on this cutoff in the impact parameter will just give us some log in the energy relative to this omega max. This omega max was this 100 GeV number that I was talking about. Okay, and then to a good approximation, I can compute the photon-photon luminosity in kind of the usual way, where I integrate over the two photon PDFs.
I missed the relation between coherence and impact parameter.
Right, because I don't want to look at impact parameters smaller than the radius of the ion.
Yeah, no,
that's the only, yeah.
Why exactly? So why the impact parameter is,
Well,
I thought the coherence is related to wavelength. Why is the impact parameter directly related to?
Well, I guess I don't want the, I don't want to look at the field. So another way to put it is I don't want to look at the field at distances smaller than the ion radius.
Okay.
So in this picture, this classical picture, the ion comes by, and I don't want to be looking inside the.
Okay.
Yeah. Maybe more accurate is to say I'm accounting for the finite size of the object. Yeah. All right. So then I have this photon-photon luminosity. So it just has the two photon PDFs and then this delta function in S hat. So this is the center of mass energy of the two photons. And just write it like this. And then with a form like this, I can also, again, easily do this integral and get photon-photon luminosity, which is this z to the fourth alpha squared times some factors, and the diphoton mass times some log stuff that I'm not going to worry about for this talk. Okay, so this is an approximation of the analytic result that gets you basically about 10 or 20% of the way to the full answer. To get a full answer, which includes things like some nuclear physics, we used a code called Starlight. It's actually written by, well, one of the people that wrote this is at LBL, which was helpful for us. And what this code does is it does a very similar calculation, but it includes a kind of form factor in these impact parameters. So the calculation it does is, instead of integrating separately in these impact parameters and just kind of factorizing the problem, you have these, if you look in the plane of, if you look in, so the beam is coming out of the board, then you have these two impact parameters, and it accounts for the fact, it includes a kind of nuclear form factor, which is a function that give as a function of the difference of these impact parameters. But so the difference between including this and just using the analytic result is only 10 or 20%, which is nice because we can understand essentially everything that's happening in this calculation.
So you're looking only at fully elastic, you don't look
Mm-hmm.
at partially inelastic? I remember from diphoton times that
Yeah.
the inelastic was actually bigger than the elastic.
Right. So there's some contribution for this lead ion to break up and emit that nucleus or neutron, and it's an order 1 fraction of the time. So I think it would be an order 1 effect, but we didn't include that because, yeah. Oh, sorry. So that effect is actually included in Starlight.
That was also protons, but I assume it's also.
Yeah. Sorry. I think that effect is actually included in Starlight. So it's not a very big effect for us. Okay, so returning to looking for a new resonance, I should also mention that this is studying the photon-photon luminosity is a there's a big literature on this subject in heavy ion collisions. There are a number of reviews. And one of the papers that kind of inspired us was a paper by Bob Kahn and David Jackson, which looked at this in the context of producing the Higgs, which almost works for SSC energies, as they found in their paper. Okay. So now the cross-section for producing the axion can be written in terms of this luminosity. And the width of the axion, so this is probably just a familiar rewriting of the usual cross-section of producing some resonance. And the width of the axion is something like ma cubed over lambda squared. But so now if I plug this luminosity in here, these factors of mass essentially cancel, and I just get that the cross-section goes as z to the fourth alpha squared over lambda squared. So you see, even for lambda of order 10 TeV, this z to the fourth factor is going to be enough to give us cross-sections of order nanobarn. And so going back to the luminosity I gave for these heavy ion collisions was of order inverse nanobarn. So that's roughly going to be enough to see several events with the current luminosity, current run, okay, with 10 TeV cutoff. And as I'll show, that's quite a bit better than some of the existing direct constraints. Oh, that's the next part. That's the next part. Oh, wait. I don't want to do this. Okay, let me do it here. Oh, uh-huh. Yeah. Oh, yeah, that was given by the 5 TeV per nucleon. You're asking why was it 3,000? Yeah. Rather than... I don't have any feeling for that, so I use this. Yeah, so sorry, it's 2.5 TeV per divided by the mass of the proton. That's all, yeah. Yeah. Oh, okay. Yeah, this was the center mass, and then per nucleon. Okay. Yeah. Yeah. Lambda, around 10 to the 4, sorry, 10 TeV, 10 to the 4 GeV. That's right, that would be more like 100 GeV, yeah. Okay, so I claim that the signal at least has observable cross-sections, and in fact the analysis for this is extremely simple. Again, I want to have a veto on any forward activity or any extra activity, and just have these two photons which are fairly central and close to back-to-back. So the ATLAS and CMS collaborations have triggers for this. So they have a trigger for 2 photons. It's greater than 2 GeV for CMS and greater than 3 GeV for ATLAS, and I'll just use that because that's the one that's already public. Okay, so again, just to reiterate, these trigger thresholds are extremely low, which is what is so extreme, which is going to help us have high acceptance for low mass axions compared to PP collisions. Okay, so I'll be able to get to 6 GeV axions roughly. The only other cuts were essentially this requirement of the photons being nearly back-to-back. So there's some delta phi less than, I don't know, something like this. This is delta phi though, so it's okay, yeah. And there's also some PT thing, but this is essentially the same as the back-to-back requirement. Okay. So great, the signal looks extremely clean, and we can definitely get it with this trigger. Now backgrounds. going to erase this. Erase this. Well, that might be helpful. I don't know how to.
Just use the other blackboard.
But it's too low, right? It's a bit too low. Okay, I'm gonna try. There's no way I can write on this, right? Okay, I'm just gonna have to erase. Okay, so the main background is actually the main background for this signal is actually another interesting signal that was observed for the first time in the Atlas paper. The main background is light by light scattering. So this was proposed a few years ago, or it was proposed a few years ago by Dantaria and his collaborator, Da Silveira, that one could actually directly observe this in heavy ion collisions. So while light by light scattering has perhaps indirectly, you can argue, been observed, at least photon-photon collisions producing diphotons has not been directly observed. So they proposed heavy ion collisions to look for this. And it is the biggest background for us, but it falls off steeply with the center of mass energy. So again, the cross-section.
So the option is for them.
Yeah, that's right. Why did they miss that background? Okay, so it's the photon-photon luminosity times. So this is the cross-section for just the photon-photon part. The total. Oops, let me write it this way. Okay, but the difference compared to the axion case is that, of course, just the naive scaling of this cross-section here is going to be alpha to the fourth over the center of mass energy. And so it's going to drop off fairly steeply with energy compared to ours, where it was roughly constant up to the log part. Another background is coming from the fact that there's a very large rate for producing light charged particles. So the E plus E minus production rate has cross-section of order 0.5 millibarn.
You have some Z in that also?
Yeah, exactly. So, yes, in all of them, yeah. So it's the same luminosity as I used before. Right, because these are fairly light, again with the Z to the fourth enhancement, this cross-section is huge. So for instance, one possible background is a fake of an electron faking a photon. But as long as the mistag rate is below about 1%, which seems very reasonable according to the, well, especially given that when Atlas published their results, and this was certainly true. But assuming that this mistag rate is below 1% or so, then this is not too important of a background. And a related background is similar. We have the E plus E minus, but we didn't. This is just a simple 1% estimate, constant in PT. The PT, of order few GeV. Yeah. I can look up between, you mean for this or for? Right, I'm going to be looking 6 to 100, but most of the luminosity is between 6 and 50, let's say, GeV. Yeah. So I can also have E plus E minus, and now an electron might spit off a photon, and the electron might be lost, but there's a hard photon, and that would also fake our signal. This is an even smaller rate because it's pretty hard to, once you require that an electron emits a hard photon, then you suppress the BREM a lot. So these are all photon-initiated processes. An unknown is how big is the hadronic contribution. So there's something like this. So these are gluons now. I'll draw these spirals better. Sorry. Here we go. So this process is something that has been calculated in proton-proton collisions, these for ultra-peripheral collisions. And it's not exactly known how it scales up for heavy ions, but the best estimate says that it scales up with a to the 2/3 times the proton-proton result. And that intuition comes from thinking about having these two heavy ions that collide, and the only part that really matters for the ultra-peripheral collision are kind of the nucleons on the outer edge. So that's the rough scaling. Okay, but with this scaling, this is definitely negligible. It can also be further cut with some of the back-to-back requirement. So this requirement also cuts down on that background a lot. Okay, so the result is that I can look at number of photons versus invariant mass. So I get these three contributing at a non-negligible amount. And so here is 15 GeV, and here's one event. So all these backgrounds drop off, and they're essentially negligible above 15 GeV, which makes the Axion search a background-free search. And at least in the most recent Atlas result, there's, I think, one event at 20 GeV, and that's it. And maybe one at 15 GeV as well. Okay. All right, so I'm going to show you our projection and the Atlas result. All right, here's mine. Okay, so this is the Axion parameter space in the mass and 1 over lambda. So this is 0.1 GeV, a few GeV, let's say 5 GeV, and 100 GeV. One other comment is that the energy resolution expected for this is, well, we assumed of order 0.5 GeV or so, but it doesn't really matter about this because, again, it's background free. So in this Axion parameter space, let me show you some of the existing constraints. So for light Axion, there are a whole array of searches and constraints. So just down here, the most relevant one is probably beam dump. So this is Dobrik et al. Beam dump. Sorry. Oh, now I can use colors. And there's this mass range between about 100 MeV and a few GeV where there's actually not that many existing constraints. So what we looked at was LEP, and we found something here, around here at the inverse TeV level. And this constraint comes from looking at associated production of the Axion. And for such low mass Axions, the diphotons are not resolved, but there's a result on the inclusive E plus E minus to 2 photons cross section, which we can use to conservatively bound this process. So that's what that is. And up here, there's another LEP thing, which is now the same process, but I've resolved the two photons. And so I'll call this opal. And above about 10 GeV, I actually do have some LHC proton-proton constraints. So above 60 GeV, I have just regular diphoton search. And down here, so this is all Atlas searches. Down here I have, for instance, it's the same process as initiated by PP collisions, where we recast a search for Higgs to 2 axions. And for this search, they only required 3 axions, so that's why it works. OK, so that's the landscape of the existing constraints. And actually, so what I discussed earlier was that with a 1/10 TeV cutoff scale, or cutoff scale of 10 TeV, I can get order nanobarn cross sections. And indeed, our projection for the result for 1 inverse nanobarn is here. Cut it off better. From heavy ion collisions. And then this is like 10 inverse nanobarn. And indeed, when the Atlas paper came out late last year, we also did a recast, and it's very close to this 1 inverse nanobarn line. They only had 0.5 inverse nanobarn, so it's slightly weaker. But yeah, so what we see is that these heavy ion collisions are significantly better than the existing proton-proton search limits, and are a complementary way to look for these axions in a much cleaner environment.
Ask why the black one constraint is brief light. If it's unresolved two photon,
Yeah.
very light mass,
Yeah.
highly boosted,
Yeah.
they should have this line. Why is it bright?
The cross section is independent of the mass. The cross section just goes as 1 over lambda squared.
But when the mass is smaller, you have a large boost. The angle is.
Oh, yeah, so we assume everywhere in this mass range it's unresolved, so it would turn off, yeah, it would start to turn off somewhere here, but at least in this mass range we assumed it's okay. Yeah, I think, yeah. And, what's I going to say?
Inverse nanobarn, like the HLLC.
That's right, yeah. That's the HLLHC. HLLHC.
Since real LHC real HLLHC will have much more luminosity than that.
That's right.
Might be better off just going to proton-proton and giving up the Z to the.
Yeah, I should.
Z squared.
Well, okay, yeah, let me mention, yeah. So this is also 8 TeV result. So first you might ask I don't think this analysis is out for 13 TeV. But the PT thresholds were already at about 20 GeV. So if that's raised, the efficiency will drop a lot. So we don't know exactly what will happen with the 13 TeV data.
No, I'm asking about your search, only with protons.
Oh, yeah, yeah. So there's a CMS proton-proton up here for exclusive proton-proton collision with like 30 inverse microbarn something. So yeah, you could picobarn? Sorry, I don't remember the number. Picobarn makes more sense. Yeah. So if you could do it, if you could do it with proton-proton, then great. But I think this was at much lower instantaneous luminosity, like different run conditions. It was from the very first, the beginning of the. Because this was done when I think the pileup conditions were much more favorable for looking at these exclusive things early on. And I'm not sure that they're planning to do that. Oh god, it's turning. It's coming off, but I'm almost done.
But they might, the free-scale trigger might be more
Thanks, Matt. Okay, so I'll just spend last few minutes discussing other possible constraints in this parameter space if you allow other interactions. I think one just to mention, because it's been done by people here, is something like Higgs to ZA. This is Bauer, Tam, and Neubert. That can cover a lot of this region if this is a separate operator. Another thing that can improve on the existing constraints are B-factory results. So we can have, from here, Babar and Bell 2 looking at this same E plus E minus to 3 photon, so 3 photon B-factory results. And finally, all of this region can be covered with rare flavor decays like B to Ka, or let's just say that. And this is coming if I have axions that couple to a W. So here's my B to S transition with a W, and the axion comes off. So it's not assuming exactly the same interaction, but this AFF operator might be coming from ABB plus AWW, in which case I would cover this whole mass range with a rare flavor decay at Babar or Bell 2. Okay, but so to go back to axions, it's a very clean search. As far as we know, it's the only BSM search with heavy ion collisions that's competitive with proton-proton searches, and it's extremely complementary. So thanks.